Last week we talked about the science of climate change, kind of the fundamental science behind global warming, why the climate is changing. I touched on impacts a little bit, but this presentation is going to be a little bit less on the fundamental science, a lot less on the fundamental science, more on the actual impacts. And I'll specify impacts to Illinois and then go a little bit broader. Although I'll say that the impacts, the global impacts that I focus on will also have an impact on Illinois. And I hopefully, talking about certain global impacts can make climate change and global warming a little bit more of a relevant topic to students and folks in Illinois, because we in this state are actually fortunately a little bit less vulnerable than other parts of the country and the world to climate change impacts. I'll talk about that just a little bit. So again, I think I showed this plot last week. This is just from different data sets showing the change in global average temperature since the late 1800s. We see that global average temperature has increased by about 0.8 to a degree Celsius, or close to 1.5 degrees Fahrenheit. That is in direct response to increased concentrations of carbon dioxide and, to a lesser extent, methane in our atmosphere. But the global climate system is complex. We have more energy entering the Earth system at the equator than at the poles because of the shape of the Earth and the revolution around the sun. That will never change, or at least not in our lifetimes. And so we have energy transfer both through the atmosphere and through the ocean, from equator to poles, to try to equalize that energy balance that will never be equalized. And it is that global transfer of energy that drives our circulation patterns, again, both atmosphere and ocean, and creates the general weather patterns. And so what that means is that an increase in global average temperature does not necessarily mean that every place is going to warm at the same speed. It definitely means that that's not the case. And because of that, we see different changes in climate that have these very complex compound effects. I saw somebody on Twitter the other day post, it was kind of a revelation to them. For climate scientists, it's kind of a duh kind of moment, but climate change is not adequately described as really climate change, because it broadens out from just changes in temperature and rainfall. However, I will talk first in this talk about temperature and rainfall, because that's really, the drivers of overall climate change. So it's kind of drive home that point that not every place on Earth is changing at the same rate. This is showing the 2007 to 2018 annual average temperature with respect to the 30-year normal from 81 to 2010. So this is showing areas that have warmed in yellow, orange, and red. We talked about Arctic amplification last week and the feedbacks that create more warming in the high latitude regions in the Arctic versus the mid latitudes or tropics. And so overall, you see that the vast majority of Earth has warmed over the last 30 years, 100 years, 150 years, but certain places have warmed at a much higher rate than others, and that's created different changes in climate. So I'm going to first start with talking about Illinois and specific changes in our climate here in Illinois and broadly in the Midwest, and first really talk about temperature. I will say, though, that over the last 100 years, really since we've been seeing the kind of the global warming signal, temperature has changed in Illinois, and I'll go to this slide here. However, the impacts of these changes have been much more modest than in other places, even within the U.S. and certainly globally. So we think about places like California, Arizona, Alaska. Those are places that temperature changes had significant effects on ecosystems, human systems, the hydrology of the region. So here in Illinois, we have seen impacts from temperature change, but they haven't been nearly to the extent of those places. So over the last 120 years, since really our records go back, statewide annual average temperature has increased by about 1/10 of a degree Fahrenheit per decade. So overall, about a degree Fahrenheit over the last 120, or degree to 1.2 degrees Fahrenheit over the last 120 years. I think I showed these figures last week, but it's good. It's worth rehashing that the warming trends in winter and spring, as you can see here in these plots on the top left, or excuse me, on the top right, they are winter and spring are warming at a much larger rate than spring and fall, or excuse me, than summer and fall. You can see here the darker shades of red in central, northwestern, southwestern Illinois in winter, and then especially in central and eastern Illinois here in spring. Those indicate quite a large rate of warming. And we don't really see that necessarily in the summer. Actually, as I mentioned before, these counties here in southern Illinois for summer and fall have actually cooled over that time period. And so overall, we have seen warming temperatures in Illinois. But to a certain extent, our systems have some resilience to those temperatures that they don't have in other places. If we break down temperature change into maximum, mean, and minimum daily temperature, we see different changes as well. So that's what this table here is showing, that overall, the change in minimum temperature is much larger than that in maximum temperature, especially in the summer and the fall. So even though I'm showing these, these maps here that don't really show that large of a change in temperature in summer and fall across the state, that's for average temperature. When we break it down into mean and maximum, minimum, maximum, minimum temperature is changing at a much larger rate than maximum temperature has. And actually, you can see here that maximum temperature during the summertime statewide has actually cooled a little bit. Now that cooling trend is not significant. It doesn't rise above the signal to noise because there's a lot of variability in summer maximum temperatures. However, what we can say with certainty is that maximum temperatures in the summertime in Illinois have not increased over the last 100 to 120 years. And most of that is due to increases in humidity. So if we think about here in Illinois, we are not water stressed very often. We have an abundance of water, and in many cases, we have an overabundance of water. So what that means is that as we increase air temperature, the amount of water vapor that air temperature can hold, the saturation vapor pressure of the air, it increases. It increases exponentially, actually. So warmer air can, quote unquote, hold more water vapor. And that relationship, in practicality, the atmosphere will follow that relationship known as Clausius-Clapeyron if we have water available. So as we continue to increase temperature, it will continue to evaporate more water, and we'll have more water vapor or humidity in the atmosphere. And so what that's meant in the summertime especially is that as temperatures have warmed, especially minimum temperatures, we increase the amount of humidity, as well as humidity being blown in from other places in the U.S. And what that does, you think about humidity, it increases the prevalence of cloud cover. So if we think about a typical summer day, cloud cover in a typical summer day will reduce the amount of shortwave radiation coming in from the sun, which will depress maximum temperature. So we just won't get as hot as we would in the afternoon as if we didn't have a lot of cloud cover. However, the reverse effect is in place during nighttime. So at nighttime, those clouds will absorb, re-radiate the outgoing long wave radiation, which will actually increase the minimum temperature. And that's what we've seen. So because of the increase in humidity and cloud cover, we see a dramatic increase in summer minimum temperatures, but actually a slight decrease in maximum temperatures. So that's really what we've seen here. And I'll contrast this with projections I'll talk about in a little bit of a future change in temperature in Illinois. So overall, we increase temperature, and one impact that has is increasing evaporation. So I call this evaporative demand, which is a little bit different than evaporation. Evaporative demand is essentially how much water vapor that the atmosphere can take in, how much evaporation it can actually take in. And I just mentioned that before about how the amount of water vapor the air can hold is going to increase as the temperature increases. And so again, because here in Illinois, we have an abundance of water. That means that we're getting more evaporation. We're getting more water transfer from the land and our water bodies, lakes, rivers, sort of thing, into the atmosphere. That's what these trends are showing here. This is just from the Illinois Climate Network station in East Peoria on the campus of ICC. That shows an increase in the average temperature that corresponds to an increase in evapotranspiration, essentially the amount of evaporation that's entering the atmosphere. We've actually seen that the trends in evaporation are now largest in the fall. We're actually increasing our amount of evaporation into the fall. So we think about our hydrology here in Illinois, we tend to, if we think about a water year starts October 1st, it ends then the following September 30th. The October 1st now and into the winter, that's our recharge phase. We tend to get more precipitation than we do evaporation, which means we have a net water surplus, right? We have more water than what we can do with, which is why it's very rare we get droughts in winter and to a lesser extent spring. But once we get to the spring and the summer, temperatures start to warm, our evaporation increases, plus we have vegetation that starts actively growing in spring, which means we increase transpiration, our amount of evaporation from those plants. And in the heart of summer, our evaporation can actually outweigh or equal our precipitation. And so we have dry down, right? And so wet and dry, wet and dry. What we're seeing because of that increase in temperature is that dry down season is lengthening. It's getting longer, and particularly into September and October when we would be typically recharging. Now, normally, because precipitation, as I'll show, is increasing, that's not really that big of a deal because we're getting more water, we're getting more precipitation, so we're not increasing the issue of drought, the risk of drought. However, when we do get a very dry fall like we had this year, late summer into fall, it does increase the chance of drought happening. There's also a number of impacts that come from changes in temperature. So I'll start with health impacts. What this map on the right-hand side is showing is tick species that were collected in 2018 from the tick collection program that's run from the University of Illinois and IDPH. And what you can see first and foremost is that Southern Illinois has more ticks than Central and Northern Illinois. Southern Illinois is because it's a more humid, warmer climate. More ticks can expand their range into Southern Illinois, and Southern Illinois has more has a better overall environment for ticks than the farmlands of Central Illinois do. So. Overall, we see more tick prevalence in Southern Illinois. But what this is showing is that the Lone Star tick, which is shown here in these pie charts in green, is expanding its range very quickly into Southern and even into Central Illinois. Now, the Lone Star tick actually spreads heartland disease, which is a serious disease that was confirmed last year for the first time in Kankakee and Williamson County, so both Northern and Southern Illinois. Lone Star ticks also bring alpha-gal, and some of you may or may not have heard of this. If you're from Southern Illinois, you probably have. Alpha-gal is the disease that makes folks allergic to an enzyme that's found in mammalian meat. So it makes folks essentially allergic to pork, beef, lamb, any sort of mammalian meat. And this is something that's increasing in prevalence quite a lot in Southern Illinois. At the same time, Lyme disease, which is spread by the black-legged ticks, those are also, the prevalence of Lyme disease is also increasing quite a bit across the state, as is West Nile virus, which is, of course, a mosquito-borne disease. And so overall, we're seeing, because of an increase in temperatures in the wintertime, we're seeing these vectors, mosquitoes and ticks in particular, they can overwinter at a higher rate, at a higher prevalence over the wintertime in Southern Illinois, and therefore can increase the incidence of the diseases that they spread into Northern and Central Illinois earlier in the spring and deeper into the fall. At the same time, because we're seeing increases in fragmentation of habitats, we're getting more host interactions with humans, hosts being birds and white-tailed deer are some of the largest hosts for these vector-borne diseases. So both things together, the development of land for agriculture and urban purposes combined with temperature and precipitation changes over the last several decades have increased the prevalence of these vector-borne diseases. Also, one to look out for, the Gulf Coast tick. This is expanding northward into Central Illinois. That's the one here in purple or magenta. And you can see that it was actually confirmed here in Champaign County for the first time this year, Gulf Coast ticks. They do carry some, and I can't remember the disease itself. I needed to go back to my entomologist friends, but we are again seeing these vector-borne diseases increase in incidence across the state directly due to climate change. We also have health risks from extreme temperatures, especially extreme heat. So increasing temperatures does, of course, as you can imagine, result in a higher risk of heat-related illness. That could be heat exhaustion, heat stroke, and heat-related casualties. What this map here on the right-hand side is showing is it's from the BRACE program from the University of Illinois at Chicago. Any of you who may be teaching or want to include health and extreme heat related issues of climate change or of climate in general, I really encourage you to visit this website at BRACE at UIC because they have a lot of really great resources available. In this case, what this is showing is the overall risk category of each county in Illinois for extreme heat related health, negative health outcomes. What they showed is that counter to intuition, the counties that had the highest risk are actually some of our most rural counties. And that's because the access to hospitals and other health related or healthcare resources in rural areas is more sparse. And therefore you have more negative health related outcomes from extreme heat in those rural counties versus urban counties, for example, like Cook or St. Clair. And so that is an important point to say, like heat related illness, when we think about extreme heat in Illinois, everybody usually goes to the 1995 Chicago heat wave, and certainly Chicago, and especially in certain neighborhoods in Chicago, they do have vulnerability to extreme heat. We'll talk about that a little bit next week in environmental justice discussions, but that it doesn't mean that our rural areas don't have that risk as well. In some cases, that risk is larger in some of our more rural areas in Illinois. Okay, so let's talk about precipitation. And I think I could say arguably, but I would say inarguably, changes in precipitation have caused the largest impacts related to climate change over the last 30 to 40 years. And it's almost entirely due to excess precipitation. So overall, Illinois is getting wetter. By about 5 inches. The total annual precipitation has increased by about half an inch per decade, or 5 inches, 5 to 6 inches over the last 100 to 120 years. Down below here, I have the table of seasonal trends. And overall, in all three regions of Illinois, northern, southern, and central Illinois, we see that the summer precipitation trends are much larger than other seasons. So summer trend is 2 to 4 times larger than that in other seasons. To give you an idea, kind of bring this home, 6 out of the top 10 wettest springs on records going back to 1895, 6 out of the top 10 in Rock Island, Aurora, and Mundelein have occurred since 2009. Southern and central Illinois are not devoid of this trend as well. For example, 8 out of the last 10 years on record in Belleville there in Southwest Illinois have been wetter than the 30-year normal. And so what that means is we're just seeing overall more precipitation, which of course leads to issues with excess water, riverine flooding, things like that. At the same time, I alluded to this last week, but we're not only seeing more precipitation overall, but we're seeing more intense precipitation. So what I'm showing you here, one way that we quantify precipitation intensity is to talk about return intervals or recurrence intervals. And so I think probably most people have heard of a 100-year flood, right? A 100-year flood is the flood level, the level of the stream height that has statistically over a long period of time has a return rate of about 1% or 1% chance of occurring any given year, right? And that's the 100-year flood. Well, we can do the same thing with precipitation. And we do. We say, what is the 1 year out to 100 or 500 year precipitation totals for a given period of time at a certain place? So what I'm showing you here on the top right here, this is a plot showing 1 day total precipitation and 5-day total precipitation in the Northeast Climate Division. That's Chicago to Rockford down to Pontiac and that kind of area of the Northeast part of the state. Estimated over different recurrence intervals, estimated from 1989 data that were current as of 1989, and the most recent estimate in 2019. Just to give you an example here, what this is showing is that the 24-hour total that represents a 10-year event, in the Northeast Climate Division. That means it has a 10% chance of happening any given year. That has increased from 1989, where it was about 4 inches. So a 4-inch rain event on a single 24-hour period had about a 10% chance of happening any given year. That's increased over the last 30 years. Oh, excuse me. That's increased over the last 30 years to over 5 inches. So just in the last 30 years, we've seen that increase by an entire inch. The same thing with the 100-year event. We've actually seen the 100-year precipitation in the Northeast Climate Division increase from a little bit less than 7 inches back in 1989 to over 9 inches now in 2019, which means that, thinking about getting 9 inches of rain in one day, that has a 1% chance of happening any given year now, which means that 100-year flood that results from those precipitation totals, that the probability of those kind of flooding events are increasing because of that. To kind of bring this home, I think I showed this table last week, but this is describing a little bit more detail. These sorts of events that we see, large flooding related impacts. For example, May of this year in Chicago, when I-80 was flooded, anytime you see interstates flooded, the flooding gets really bad. They had 8 inches, almost 8 inches of rain in 4 days. And based on the difference between the 1989 estimate and the 2019 estimate, the probability of that occurring in any given year has doubled in the last 30 years. Quincy, actually, I only included one event from this year in Quincy, although they had 2. They had almost 7 inches in 4 days. That also, the probability of that has doubled over the last 30 years. And I know a lot of you who are from the Peoria area were talking about flooding this year. The flooding that happened in Peoria, this one here in July, early July this year, almost 6 inches of rain in 6 hours, which is absolutely incredible. That was a 250-year event 30 years ago. It's now gone down to a 100-year event, which means that all of the flooding that occurred as a result of that event in Peoria has a 1% chance of happening any given year. So if you think about your risk, home insurance, car insurance, agriculture, crop insurance, right? You're thinking about the probability of that happening. This is really, I would say, the largest impact to Illinois is from flooding because of that increase in precipitation intensity. And so, I don't want to spend too much time on this slide, but what this is suggesting, what this is showing is that how much runoff we have, basically how much water is running over the land surface as opposed to infiltrating into the soil. That's directly related to the rainfall intensity. So Q is our runoff here, and it's equal to the runoff coefficient, which is essentially your land cover, and that we can assume that stays constant, times your watershed area, which is staying constant, times the rainfall intensity. So it's a simple multiplicative relationship. If we increase rainfall intensity, we're going to increase that runoff. That's kind of a double-edged sword, because not only do you get the runoff from agricultural fields such as this, which increases flooding, which has a water quantity problem. Of course, you just have too much water on your fields, in your homes. You also have a water quality problem, because it's not just water that's running off of these fields, it's nutrients as well. But at the same time, if we're going to get those 5-6 inch rainfall events in the summertime and the spring, and then go longer in between rainfall events, it means that your soil is netting overall less water, which makes your ecosystem, your ag system, your hydrologic system less resilient to drought and dry spells because of that rainfall intensity. I'm not going to spend too much time on snowfall, just because we haven't really seen a whole lot of change in snowfall. In Southern Illinois, snowfall has decreased over the last 50 to 60 years. I can't go back 100 years with snowfall observations, just because the observations back then weren't so great. But over the last 50, 60 years, we have seen a decrease in snowfall, total snowfall and snowfall occurrence or frequency in Southern Illinois. That is pretty much south of I-64. In Central and Northern Illinois, the time series are too dominated by variability. I show that here. This is showing 5-year averages of total annual snowfall from the Peoria airport. And you can see, the 1970s, those of you who are around then can remember those winters were extremely harsh. And had a lot of snowfall. And then more recent winters, 2012 or 2010, 2011, 2013, 14, and then 2014, 15 did have a lot of snowfall. And so what this means is that overall, there's not much of a trend in snowfall when you get north of I-64. part of that is related to the relationship between total snowfall and temperature. This is a really interesting figure that was published by Bob Davis back in 1999, where he took a bunch of stations all across the US and Canada and plotted each year temperature, average winter temperature, and snowfall, snow water equivalent. And what you can see here is as we get really cold temperatures, minus 50, 60 degrees Fahrenheit, the atmosphere just doesn't contain enough water to snow much. Whereas when we get above freezing, that 0 Celsius, 32 Fahrenheit, it's too warm for that snow. It's going to fall as rain, freezing rain, or sleet. It's really this peak right here, that kind of 32 to maybe 26, 27 degrees Fahrenheit. That's your sweet spot. What that means is that in northern Illinois, where maximum temperatures regularly fall below that threshold, by warming those winter temperatures, it actually makes for a higher frequency of days in this range in northern and central Illinois, which can actually produce more snow. So that's part of the reason why we haven't seen that large decrease in snowfall, because in Illinois, in northern and central Illinois, we actually have more of our winter season that's spending time in that kind of so-called sweet spot with our snowfall. Somebody asked last week about hurricanes in storms, so we could talk a little bit about changes in storms. This is kind of where we shift a little bit away from Illinois. We have seen overall increased Atlantic hurricane activity since 1970, so hurricanes in the Atlantic have become more frequent. Certainly, if we fit a trend line ending in this year, we're going to see that, because we've broken the record or tied the record for named storms this year. But I would say overall, the most concerning trend with hurricanes has not been their frequency, but with the intensity of the rainfall that they produced. So there's been a large increase in tropical cyclone precipitation intensity. And so what that's meant is that we're seeing, even with an increased frequency of hurricanes and tropical cyclones, we're not seeing an overall increase in landfalling hurricanes, so those that actually reach land in the Caribbean or here in the US. What we are seeing is that those systems, those hurricanes or tropical storms that are reaching land, are producing a lot more precipitation. What the figure on the right-hand side is showing is anywhere in, you can imagine it's kind of a weird figure, but this is the center of the storm here at 0, 0 in these plots. And anywhere in green outside of that area, that's where we're seeing increased rainfall that's directly attributable to climate change. So when we think back to recent events like Hurricane Harvey, or this year Hurricane Laura, those hurricanes are producing much larger totals of rainfall, much more intense rainfall. And actually, Hurricane Harvey, the amount of rainfall that it produced, about 16 inches of rainfall over a 36-hour period in Houston, over a very large area of the Houston area, that actually approached our understanding of the theoretical limit of how much rain can actually fall from the atmosphere over that time period, over that large of an area. And so that's really the most concerning trend with hurricanes, is that they're producing so much more rain that they're causing significant inland flooding. Part of that's actually related to this global slowing of tropical storms. And so what this figure on the right-hand side is showing is that overall, both in the Atlantic and in the Pacific, tropical storms and hurricanes are moving more slowly. So if you think about what that produces with rain, if you have a hurricane or tropical cyclone sitting over your house, your area, for 6 hours producing rain, or for 12 hours producing rain, your overall total rainfall is going to be a lot more the slower the hurricane moves. And that's what we saw with Hurricane Harvey. Hurricane Harvey sat in the same place. It actually, the center of Hurricane Harvey moved about 12 miles in 4 days, which is like glacial pace. And what that did is it meant that it brought a tremendous amount of rainfall because it just kept producing rain. It sat in one place. So that is actually related to global warming and changes in energy transfer, that's translating to this global slowing of hurricanes, which is again producing overall more precipitation. Okay, so now I'm going to move into projections. So what I talked about there was more historical changes, what we've seen in the last 100 years. Now we're going to talk about what we expect to see into the future. So climate projections are predictions of what we expect to happen under a set of assumptions. So they are not forecasts. Forecasts are, here's what we know today. Now let's run the model out and see what it says we think is going to happen. A projection is, here's what we know today, and here's what we think is going to change into the future. So let's run the simulation under that assumption. The assumptions that we run our climate model projections or simulations under vary in the amount of greenhouse gas concentrations between now and the end of the century, as well as various other things like land cover change, urbanization, population growth. All that's rolled into what we call representative concentration pathways, or RCPs. And these RCPs are used to run all of these different models, many different models and many different model ensembles, different pieces of the model out in time. In general, we use one of three different representative concentration pathways: these RCP 4.5, RCP 6.0, and RCP 8.5. And what those numbers 4.5, 6, and 8.5 referred to is the amount of radiative forcing by 2100 that's caused by an increase in greenhouse gases. So if we produce more greenhouse gas emissions between now and 2100, we're going to have a higher radiative forcing. So 8.5, RCP 8.5, is often thought of as the business as usual or the very high emission scenario, right? We just keep producing emissions that at our historic, 25, 30-year average levels all the way up until 2100. Obviously, under that, we're going to see larger amounts of global warming and larger amounts of climate change in general. The RCP 4.5 is the lower emission scenario. We curb emissions significantly by about 2025, 2030, and reducing global emissions altogether by the year 2100. Okay. Now, to give you specifics, RCP 8.5, CO2 levels rise to about 936 parts per million by 2100. RCP 4.5, the low emission scenario, we get to about 550. If you remember, right now we're about 420 parts per million. So, we also have to talk about uncertainty. Uncertainty in these projections, because they are projections. We're predicting the future, which means there's going to be uncertainty that doesn't come along with just observing the past. Projection uncertainty comes from three sources. There's internal variability, which is just the climate variability. We know that despite warming trends, we still get cold years. We still get cold air outbreaks, like what we experienced over the last couple days when it seemed like the temperature didn't get above 40 degrees, at least here in Champaign. We still get those despite the warming. So there's inherent climate variability that is always going to be there. We also have model variability, or what's also called model spread. Different models see things and represent things in different ways. So if you run simulations using 100 different models, you're going to get a spread, right? And then we also get what's most important, I would say, in understanding climate change, which is our RCP scenario variability. So how much spread is there between the low emission scenario and the high emission scenario? And that difference gives us an idea for how much climate change or how much global warming actually will impact the climate change effects. What you can see here from this plot on the right-hand side is that between when the simulations from the models start at our current time period, all the way out to about 2050 in the simulation, the projections are dominated by climate variability and model spread, which means that we can't really get a good signal for climate change projections until we get out to the latter half of the 21st century. So I hear from people a lot to say, like, it doesn't help me to know what temperature is going to be like in 2100. I'd rather know what it's going to be like in 2030. The problem is that the signal for how climate is expected to change really doesn't rise above the variability in the climate until we get out beyond the year 2050. So that's why we always see these kind of projections go out to 2100. So let's talk about Illinois for a little bit. What these plots are showing for temperature, on the left-hand side, we have northern on the top, central Illinois in the middle, southern Illinois on the bottom. So it's geographically staggered there. What this is showing is projections and the spread of the projections in temperature on the left-hand side, just mean temperature. And on the right-hand side, the number of days where our max temperature gets above 95 degrees each year. So what we can see overall, the red shaded areas, that's for the high emission scenario. The green is for the low emission scenario. So overall, we see not only a projected increase in mean temperature, but a large increase in the number of days that get above our 95-degree threshold in northern, central, and southern Illinois. What's very important, though, is again, beyond 2060 to the period 2100, we see the red area and the green area diverge a lot. What that means is that the magnitude of that temperature change, how much our temperature changes, how many additional days we get over 95 degrees, varies very strongly with our emission scenario, which means that fewer emissions now to the end of the century means less warming. We have high certainty of that fewer emissions will result in less warming of temperatures. And of course, then a lower impact of, a lower magnitude of impacts, health-related impacts like I talked about before. Precipitation's not so clear. Overall, projections suggest that precipitation is going to increase, going to continue to increase in Illinois. So this is under the lower emission scenario at the top, and under the high emission scenario at the bottom. The right-hand side's late century, so by 2100. The left is mid-century. Overall, we see northern Illinois is projected to get wetter. The trends are larger in northern Illinois than central and southern Illinois. But overall, the state is expected to continue to get wetter, and precipitation intensity is also projected to increase. So essentially, the trends that we have seen over the last 100 years in Illinois with precipitation are expected to continue in their magnitude. Now, with that being said, with temperature, I didn't show a seasonality in temperature because it's essentially the same. Winter, spring, summer, fall, they're all projected to get warmer. A little bit of a different rate, but they're all projected to get warmer. Precipitation is not that simple. You can see the blue colors here, the green colors. Precipitation throughout the state is expected to increase in winter, spring, and to a lesser extent fall, but summer precipitation is actually projected to decrease. So what this is suggesting from these models is that we're shaping up in the next coming decades to have a higher risk of very wet winter and spring, followed by a very dry summer. We can think about this year as an analog. And actually, I've been running around the state, not literally, virtually running around the state, using this year as an analog. In most areas of the state, especially north of I-70, we had an extremely wet spring followed by a very, very dry summer. And if you're not a farmer, you may have not known that because there weren't really impacts related to that, as far as there may have been some folks flooded in the spring or from that. But for agriculture, going from wet spring to dry summer, that has a significant impact. And that's what we saw this year when the top was taken off of yields of beans and corn, and specialty crops suffered because we had a very wet spring followed by a very dry summer. And that's what projections are showing will likely increase in magnitude into the future. Okay, so I'm going to end talking about a couple of different impacts related to climate change that transcend Illinois, transcend the US. I talked about global sea level rise. And I'm going to be the person who tries to integrate something, let's see here. I'm going to try to do a live demonstration, which as teachers never works, but I'm going to try to do it anyway here. Okay. Can somebody unmute themselves and tell me if you see a map of the US right now?
Yes, we can see it.
Awesome. All right. So this is the sea level rise viewer from NASA. And what we can do is we can zoom into different parts of the US. And what this allows us to do is to see current sea level rise and then project out changes in sea level rise based off of projections of how much sea level rise will change into the future. It is expected that sea level will increase by about 1 to 2 feet by 2075 and up to 3 to 4 feet by 2100. If we do that, if we raise sea level by 2 feet, what we see here is the change, and I'm just looking at South Beach here in Miami. These areas that weren't inundated before become regularly inundated. Now, this isn't showing, if we move up to 2 feet again, this isn't showing areas that just have a higher frequency of what they call sunny day flooding in Florida. That's already happening. These are areas that will be underwater with a 2-foot sea level rise. I can go out to one of the most fascinating places in the world, if not the US, New Orleans, which the majority of the city sits below sea level, and we can see the same thing here. If we go from no sea level rise here, current sea levels, this is the Mississippi River, by the way, there's your French Quarter, up to 2 feet, we can see some pretty significant flooding here along the main routes of the Mississippi River here. The same thing for Lower Manhattan. I actually did a Skype a scientist the other day with some kids in a classroom from Long Island. They are from the north edge of Long Island, which actually seems to fare well or better. But the same thing here, where if we increase sea level rise, we see larger inundation of these areas. Now, the problem here with that, of course, is that when we have people getting inundated with increases in sea level, what that does is it can of course, it increases the frequency of flooding, but it also results in a large displacement of people. And that's what I mentioned last week, and I want to hit on this a little bit more today, is that global sea level rise, I would argue, is the greatest threat of climate change globally, because not only does it increase the impact of things like extreme weather events, but it also increases displacement, both due to inundation because of sea level rise and due to natural disasters that are magnified by sea level rise itself. And I mentioned 1 million people were displaced in 2018 just due to natural disasters alone in the United States, not even globally. And the reason I say this is the largest, or for me, the largest concern of climate change, and not just where places will be underwater like the South Pacific, but here in Illinois that doesn't actually directly experience the role or the impacts of sea level rise, is because of our political systems. And not just in the US, but globally, one of the largest causes of global conflict, whether that means war or just conflict within developing or developed nations, is immigration. And the projections from sea level rise alone are indicating that we will see several million refugees and folks displaced globally by 2030. So by the end of this next decade, we're going to see tens of millions of people having to move, to migrate. And by the end of the century, that number rises to over 1 billion people. And so what that means for the current global political system is not necessarily, that's what concerns me the most about climate change. And so again, when we think about global sea level rise, it's easy living here in Illinois, and my students at SIU did this all the time. They just didn't really care all that much, because it's like, well, I live in Chicago, I live in Rockford, I live in Carbondale, you know, we don't have a sea near us, and lake levels aren't necessarily projected to rise incredibly. But you know, climate change works in mysterious ways, and so the impacts, even if they're indirect, will be large because of that. All right, so the last couple things, and I'm going to just breeze through these here because I'm running out of time, but also I'm going to hit up these sorts of issues more next week when we talk about environmental justice and climate justice. But, you know, climate change, of course, has indirect impacts. It has disproportionate impacts. So what this is showing in the top left-hand corner is the percent of total income that folks spend on food in different regions of the world. So sub-Saharan Africa, South Asia, East Asia, Pacific, Latin America, and the Caribbean. And what you can see is across all of these regions, these very diverse regions, the poorest spend their largest proportion of income on food, which means that it is the poorest that are at the largest risk of becoming food insecure. Now, climate change, as a result of more extreme weather as a result of global sea level rise, and global conflict is expected to result in a dramatic increase in food prices. That's what's shown here on the bottom left. However, once again, those effects aren't felt the same rate everywhere. It is sub-Saharan Africa, one of the poorest places on earth, that is expected to see the largest rise in food prices. So not only are we seeing a disproportionate level of income that is spent on food, again, disproportionately on the poor, burdening the poor, but we're seeing the poorest regions of the world where we're seeing the largest increase in food prices. And that's because their systems are not resilient or not as resilient as ours to the impacts of climate change. Same thing goes for healthcare expenditure. So the lower income bracket, and this is within the United States as well as globally, lower and lower middle income brackets spend the largest proportion on healthcare, which means that, again, if we see food prices increase, it disproportionately falls on those that have to spend a large proportion of their income on things like healthcare, which of course exacerbates a health-related issue from climate change as well. And what this means is that overall risk management, so not only are we seeing a larger overall risk of to these places like sub-Saharan Africa, part of the Middle East, versus developed nations in North America, Europe, Australia, and Asia. But we're also seeing that their risk capacity, essentially their resiliency, is also decreased relative to ours. So they just aren't able to deal with, their systems aren't resilient enough to deal with these sorts of issues, which again results in overall much higher vulnerability, but also global conflict. I'll skip through that, and we'll talk next week more about how we quantify risk to climate change. And again, we think about risk as, okay, is there going to be a tornado that hits my house? Is there going to be flooding at my house or at my school or wherever? That's the hazard part of it. But risk is really hazard that's then multiplied by vulnerability, which vulnerability is, of course, the hazard itself, but also the system's ability to deal with that hazard. So if you have a basement, you overall have less vulnerability to a tornado than somebody who lives in for example, a mobile home. And so it's important to recognize that it's not only the climate change related to the hazard itself, making hurricanes more frequent, making flooding more frequent, but also related to increased food prices, which overall increases vulnerability to something like global conflict. So with that, overall, I'll just summarize. So climate change impacts, they're wide ranging, they're diverse. It's not just temperature and precipitation. However, in Illinois, temperature and precipitation, as we summarize, have increased over the past 100 years. Projections indicate further temperature changes and likely continued increased precipitation in the spring, decrease in the summer throughout the 21st century. The impacts to health, energy, agriculture, they're expected to worsen from changes in climate over the next few decades, not just in Illinois, but globally. And then I would say, again, to bring home the point that globally, sea level rise is a serious threat to billions of people globally. And when combined with increased extreme weather frequency, could result in permanent displacement of millions by 2050 here. That's tens of millions by 2050, millions by the end of this century, or the end of this decade. So again, a serious threat that is an impact to all, even those that aren't directly affected by global sea level rise. So with that, I'll end it. I'm happy to take any questions. And again, thank you very much for letting me talk today.